So, hello everyone. My name is Rees. I work at a company called TOffeeAM. We're based in London. I'm going to talk a little bit about what we do and why we think it's important for the future of sort of like advanced manufacturing and especially high-value engineering. So, we do engineering design to physics-driven optimization. Let's go. Okay, going old-fashioned way. All right, so what do we do? Right, so we're based in London. We started in 2020. We're fortunate enough to have grown quite rapidly. We're now 20 employees. We produce a CAE tool, right? So that's what we do. We sell this primarily to large engineering companies who really need some sort of way of adding valuable increments to the performance of their components. So these are, I'll stand closer to the microphone. All right, so these are people like aerospace manufacturers, automotive manufacturers, this sort of thing. And our software is unique because, well, we leverage high-fidelity physics simulations to basically improve our designs, optimize the performance of components, and so on. We're a cloud-based service. I'll talk about why that is in a moment, but there are two very good reasons for this. And who are we? Fundamentally, we're just engineers, mathematicians. We like to solve problems. So this talk might be a little bit more numbersy and color, engineering diagramsy than the ones we've seen before. So please forgive me for that. Okay, so why do we start? Like, why does TOffeeAM exist? Why do we think what we do is important? So fundamentally, what we're trying to do is fix this problem, right? That the design process for these sorts of components is actually really time-consuming, and as a result, quite expensive. So the way this normally works is you never really start from a blank sheet design. You start from an existing design because you want to sort of minimize the risk involved because these are very expensive projects. What you do then is you update your design, you run a couple computer simulations, you see the performance, you change the design, you go through this loop a few times, and eventually you get to the point where you want to run an experimental test. You run the experimental test, and you go through this whole loop again, right? So you've been going at this for a few months now. Eventually, cool. All right, so that's the problem. Go away. Eventually, you run out of money, and then you have no choice really but to go to market. And then you sort of get customer feedback, you go round and round, and hopefully in the end you make a little bit of money. And this really limits the designs you can explore, right? So if you can only iterate 3 or 4 times in sort of a design cycle, the designs you can explore and hence the performance you can achieve is actually quite limited. Okay. So performance limitations, this is kind of like what we're trying to do. So what sort of software can we produce to sort of like accelerate this process? So one of the tools available to us, and I think probably quite a lot of people are going to be familiar with topology optimization, but I'll go through like the basics of it anyway. Topology optimization it's sort of a mathematical method for calculating the optimal distribution of a solid, of a material in a space based on some instruction that you give to it. Right, so you'll see a lot of structural topology optimization. So if you go to the Altair stand, for example, you'll see lots of like printed models of like brackets and this sort of thing. And you're basically asking the software to say, maximize the strength of this part and minimize the weight. And the part needs to be this big. Okay, so that's kind of what it does, right? And this is why it's so great. So you can say what is best for you, right? So if you're an aerospace company, best is the strength divided by the weight or something like this. So this is all good, but you don't see a lot of topology optimized parts sort of in production out in the real world, right? So there's a couple of reasons for this. First is it's challenging to set up these things. This is fundamentally quite an advanced bit of mathematical machinery, and you need to know a lot about mathematics, physics, and also just plain old engineering to actually use this correctly. At the moment, primarily people use it to solve structural problems, so other engineering problems like fluid dynamics or thermodynamics, these sorts of things. No one's really tried to attack these problems with topology optimization before. Computational demands are big. Cloud service. Real-world requirements also are not often taken into consideration, right? So things like cost-effective manufacturing, lifetime, sort of cost, constraints associated with the limitations of the manufacturing process. These are actually quite advanced, and really only people are only really starting to think about these things now. And also, as sort of related to the first part, is you need a lot of very smart people to actually get useful results out of topology optimization process, right? So let's just talk to you through like the process that you might follow, right? You start with an existing design, okay, as we discussed. You do a sort of analysis on it, right? So you notice here we've got sort of like stress concentrations, right? These big red things. This is bad. We don't want this. You run it through topology optimization software. You get this sort of crazy organic design that maybe if you're lucky, you can manufacture it using additive, but this is very expensive. For a bracket, you need to produce 300,000 of, so you got to redesign it. So you manually redesign it as a sort of inspired by TO, and then you can sort of prove it out, right? And so this is kind of like the standard TO workflow, and you can understand why maybe this hasn't caught on as much as it could. So what is the future of TO? How do we solve all these problems? So this is what we think the future of TO looks like. So first of all, you need to be able to model all of the physics, right? All of the relevant engineering physics. For us, we come primarily in Toffee, we come from an aerospace background, so that means a lot of fluid dynamics, a lot of thermodynamics, but also other interesting things, scalar transport, heat transfer, structural analysis, obviously, process modeling for chemical engineers. And also you need to be able to do many different things, right? It's not enough just to say, maximize my strength. So you want to be able to say, for my heat exchanger, I need to minimize the pressure losses of the fluids. I need to maximize the heat transfer. I need to minimize thermal stresses. I need to make sure the temperature never goes above this value in this region, and so on. And that's kind of like what we do. That's what we think we should be doing. We also need to automate and integrate the workflow with people's existing engineering workflows, right? So this means defining best practices so that almost any sort of generic design engineer can pick it up and run with it and do their job and not have to become an expert in whatever bit of physics they're working on at the moment. We need common file formats as inputs and outputs, right? So this is obviously really important. And also we need, a nice way of interacting with these things, and so it doesn't look like some sort of 80s computer with like 1 million bells and whistles. Cloud-based service, right? So compute, really expensive, put it on the cloud, infinite compute. Price comes down, it's accessible to people who cannot afford to buy a massive HPC system. And also, what's really important for us is it means we can be reactive to our customer demands, right? So this is, I think, just in general for software, if you can respond to your customer as quickly as possible and not have to sort of wait 6 months for the next release in June, this is really quite powerful and important. And finally, keep it real, right? We're not making pretty pictures, we're making parts, right? You need to be able to manufacture them. You need to be able to optimize for cost. You need to be able to optimize for different operating conditions, right? In an airplane, doesn't spend its whole time cruising. It needs to taxi, it needs to take off, it needs to land, it needs to operate in emergency conditions. And all your parts need to work for all of these situations. So I'm going to talk about 2 sort of case studies right now that we've worked with our customers. And they're both primarily looking at a quite sort of relevant topic right now, which is just electrification. And so I'm going to look at a case for electrification in cars and electrification in aircraft. And then after that, I'll talk a little bit about sort of the next steps, right? So first is a case that we did with Ricoh. So I think they're here as well. We might be hanging around their booth. Okay, they want a heat sink for a CPU, essentially. Okay. Oh boy. Okay, so they want a heat sink for CPU in an electric vehicle. They had an existing design. They wanted to use some specific additive process to manufacture it. And they just said, can you do it? All right. And we said, we probably can. So this is kind of like a conventional design for this sort of heat sink, right? So you have like a heat source in the middle. So this is your CPU. And then you bolt a fan to it. And this sort of design makes a very high surface area, right? So if you have a high surface area, you're dissipating a lot of heat. This is very convenient. And the other thing about this is it can be manufactured using just an extrusion process, which is really cheap. And so you can mass produce these things. So Ricoh wanted something different. They wanted a much higher performance, and they were willing to pay for it with a much more expensive manufacturing process called binder jetting. So we put this into TOffeeAM, and we get this sort of crazy design, right? So this is based on simulations of the fluid dynamics and the thermodynamics, and asking it to minimize the temperature of the chip and also minimize the power necessary to produce the flow by the fan, right? So this is a design made for aluminium binder jetting, and also we sort of maximized the heat transfer. I don't know the numbers, and I would have brought them with me, but I'm not sure we're allowed to show them yet, but I've been told it's much, much better than this guy here. And then they printed it, so we might even get some experimental results. So this is the printed part. I think it's going to be at Forum Next, if anyone's going to Forum Next, so you can go have a look at it. And it's all very good. So this is kind of like what we did with Rico. We took their sort of existing sort of heatsink design, produced a sort of much improved design that could be produced with their binder jetting process. But I think probably some of you are probably thinking, okay, it's maybe a little bit unfair to compare this sort of cheap, high, high volume production extruded heatsink to this sort of really specialized, expensive additive heatsink. Well, okay, we've thought of that as well. And like I mentioned earlier, we think one of the most important things to sort of like really get topology optimization out there as a product, as a tool for engineers to use, is to be able to allow engineers to specify constraints on their designs to make sure they can produce with any sort of manufacturing process they want. And so you can do that with TOffeeAM as well. So this is essentially, fundamentally, a 2D design. Same sort of physics model, same sort of everything, except we've just said, make it extrudable. You can control things like feature sizes here. So if you want fine features, it's going to be more expensive. If you want to make it cheaper, you can set this feature size to a coarser level. And you can control all of these things and make basically exactly the part you need with the performances you need. So this is what we've done for Rico. So, and then the next thing I want to talk about is electrification for aircraft. So this is a project we did with Rolls-Royce. And if you really want to get to the technical details, we published a paper about it in ASME Turbo Expo. But they came to us with this basically battery coolant system. They've got 3 cells, and these are the conditions. Okay, so they give us all these sorts of crazy water, ethylene glycol fluids, and they have a specific aluminium alloy they want to use. And they gave us requirements saying, okay, here's the power. We would want to maximize the heat transfer away from these things. We want to manufacture it using a milling process, all these sorts of things. So we put this into our software, put all this data into our software, and the pumping power necessary, 65% lower. Temperature across the board was lower on average. Lighter by almost 40%. So you can imagine for something that needs to fly, this is quite exciting. And also, they can manufacture it using their milling techniques. So how did we get here, right? So first, like I said, we model everything, the solid dynamics, the thermodynamics, the fluid dynamics. We can limit the complexity into 2D, 3D. We can control feature sizes. We can constrain the weight of the part. If you know your part cannot weigh more than X kilograms, you can say, please, I want my part not to weigh more than X kilograms. And sometimes this is not possible, and then it won't work. But if you know it's possible, it'll do it for you. We can export it as a CAD file, right? So there's no reverse engineering of meshes, which is often a problem with these sorts of topology optimization stuff. We provide simulation data in open source VTK formats, so anyone can have a look at the fields of the pressure and the temperature and basically check that we're not just making up numbers. And we can ensure manufacturability by setting mill or CNC bit size, and also we could even manufacture for cost, right? So how long does it take to mill out one of these parts on your machine? Okay, right, and I've got some more pictures here. Okay, so here's the pressure. You can see basically there's a big gradient in color on the existing design and the pressure, and here we've basically got uniform pressure, so there's no pressure drop. And then this is kind of like the difference between sort of running without any sort of control on the bit size for the CNC or the mill, and this is with the control, right? So this is probably slightly more performant, right? You're going to get a higher heat transfer here, but ideally you want to have a real part, so you got to do that. Okay, so this is like 2 case studies. I just sort of like put in bold. This is a slide I showed earlier, and I put in bold sort of like the things we've tried to address. Fun. And there's a couple things I haven't talked about yet, sort of like our user interface, but it's cloud-based, so if you want to see it, come speak to me and I'll get it up on my iPad. haven't really talked about robust design or any other physics models, but the last few slides here, I'm going to talk about like where do we see the future? Like what can we add to this, right? So we've already had a lot of success, but this is not enough. We want to keep going. We want to really get it out there. And the first is basically additional physics models, right? So the first, I think, is turbulence. So I don't want to get too deep into it, but basically turbulence models in these sorts of internal systems, heat exchangers, these sorts of things, the turbulence models that people use are not very good at these things, right? So on the left here is kind of like, these colors are basically how turbulent the fluid is, right? So on the left is the truth. This is a really, really high fidelity simulation with no models. On the right is a common model that most people use. You can tell they're very different. And we've developed a sort of physics-informed neural network, which basically learns from this, tells you this is what I think it is, and it's much better than this, right? So this is important both for calculating, your performance and also your heat transfer, right? Turbulence is very important for heat transfer. But there's also just other stuff, right? So buoyancy is very important if you want to do sort of like passive heat sinks and this sort of thing. But we're also working on other things, like I mentioned earlier, process models for chemical engineering and this sort of thing. Other thing we want to add is additional optimization options. So two-fluid heat exchangers, obviously massive market. So we're developing that, right? So if you imagine you've got two fluids, a hot one and a cold one, oil and fuel, oil and air, and you need to cool the hot one, and you want to make a design, well, ideally, you would simulate the physics of both, and not just one and then the other. So that's something we're developing. And this is kind of like what you get out of it. This is like a solid part, a membrane separating the two fluids. And then that's what the fluids look like. This is all very good. Fluid structure interactions. Thermal stresses are important. Pressure stresses are important. We need to be able to model these. This is a design of some sort of coolant system. This is the temperature distribution. And if you look closely, you can see like the design that we generated. And these are the thermal and pressure stresses. And so what this means is we can use this to control wall thickness and minimize stresses and so on. That's very difficult. That's all I have to say about that. And finally, we just want to be able to let our customers use our software for far more things, many more manufacturing methods, allow them to control many more things. So the first is obviously overhang minimization for additive, right? So this is basically an existing design, and we said no overhanging regions of more than 45 degrees, and it's made a small tweak, but now it's no longer overhanging by 45 degrees. Minimizing shrinkage and warpage, residual stress minimization. This is the same, actually, this is all the same thing, right? This is all the same optimization. This is kind of like a baseline, and you can see this is sort of like basically a measure of the stresses caused by shrinkage. And we can minimize that by applying this constraint, and okay, it looks much better. And finally, CNC 3-axis, N-axis CNC machining, for example, is another thing, but there's also other things we work on, like casting and so on. And then finally, all these other things were really cool to have, uncertainty and so on. Okay, so that's it. This is kind of like where we think we're going. And we think we can add the most value to these large engineering companies. That's us. I'll take questions.